Hi, we're the Baymar team, and this is our presentation of our boat bumper design for the November OpenWERX Challenge. I'm Andrew McCutcheon, the owner of Baymar Solutions, and myself and Michael Barry were the main team, though the extended team participated in the brainstorming session. Baymar is a mechanical engineering development company with contract assembly and CNC machining capabilities as well. We predominantly work with heavily regulated industries such as defense, aerospace, and medical device companies. I'm a mechanical engineer from the University of Arizona, and I started Baymar over 10 years ago. Michael is a mechanical engineer from the University of South Florida and has been with Baymar for 3 years now. The primary goal of the challenge was to safely transfer personnel from the vessel to the target and to protect the bow of the vessel from damage while it's pinned against the target. The requirements were that in a sea state of 3, one person should be able to install the system in 5 minutes at night with gloves on. The system should be capable of being stored in a 4x4x2 hatch area. We must use available tie downs on the vessel. We cannot install any mounting hardware. And the device must sustain a 5,000 pound static load with an additional dynamic load of 1,000 pounds at 1 hertz. We looked across many industries for inspiration, and our team came up with a lot of different options to explore. Several different spring mechanisms were discussed. The foam, like what is used in car bumpers. Polymer lattice configurations, such as the wheel shown in the picture. Inflatable buoys or bladders, and even a pneumatic cylinder structure. Once we had all these ideas identified, we used a Pew analysis to rank each idea against the different requirements. We assigned a weight for requirements that we felt were more important than others, and then graded each idea against each requirement. What resulted showed the top 3 ideas as an inflatable buoy or bladder system, the polymer lattice, and the EPP foam solution. So we explored each of these in greater detail. Started out with the inflatable bladder. While investigating inflatable bladders, we realized that any bladder shape will essentially turn into a sphere when inflated, thus requiring internal supports to maintain shape. With inflatable mattresses, this is accomplished using heat stake or ultrasonic welding to properly attach internal supports. However, due to the high strength required in this application, a polymer impregnated fabric would need to be used, thus removing the option for simple heat stake or ultrasonic welding. The fabric would need to be sewn in place. To maintain an airtight seam across all of the supports would be a very time and cost prohibitive solution. To get around this, we thought of using easily made and sealed cylinders, which would then be held together by a sheath. Unfortunately, if all the chambers were connected, a single puncture would be catastrophic. And if each bladder was separate, then the system needed to inflate all of them at once while also keeping the air from flowing from one chamber to the next after a puncture would be complicated. Even after such a system would be designed, the construction of such a system would be non-trivial. This also requires power and air to support it, which adds additional complexity and ultimately would reduce reliability of this system. So we moved on to the polymer lattice and EPP foam solutions. Polymer lattice seemed like a good idea as well. It was extremely durable, puncture resistant, and would have good stability for personnel transport. However, as we got it modeled, we realized it was going to be heavier than expected at 80+ pounds. So we began optimizing the lattice to reduce the weight, but this increased the complexity. Then as we began to think ahead to manufacturability, we realized that it would be a very expensive and complex mold to produce such a large lattice. If we broke it into smaller lattice pieces, then it takes longer to assemble, and more importantly, it weakens the overall structure, making it not as rugged. And then it hit us. The ultimate honeycomb would be to use an expanded polymer, which could be molded in one shot. The solution is a lightweight expanded polymer, more specifically an EPP, wrapped in a durable, non-slip, rubberized nylon and Kevlar blended weave. There are multiple layers of varying materials and densities, allowing for excellent strength and impact resistance while staying lightweight. It can very quickly be deployed by removing the 48-pound package from the 4x4x2 stowage area, clipping the straps to the 2 existing mounting points with a quick carabiner style clip, then deploying the block over the bow and cinching the straps with a cam-style quick cinch system. If the seas are rough, the operator can set the block on the deck and clip the straps first, securing it to the deck. So even if a wave comes along or rough seas are tossing the vessel around, the block's not going to fall off into the ocean. It's going to still be attached to the boat. There's no need to clip on the tow eye because the design will wedge itself on the bow with the tension provided by the straps. This will provide a very stable surface with no bounce and limited compression movement for the operators to move quickly and safely to the target. The simplicity of the system results in high reliability and quick and easy deployment. The construction results in a very durable solution that can take big impacts and a lot of abuse and stay functional. The layers consist of the Abrasion Shield on the front, which is super durable and helps distribute point forces across a wider area. This is followed by a high density section, which is 4 times stronger and more resilient than the very durable EPP foam. Behind that is what absorbs most of the impact and provides the surface for the operators to walk across. It's very lightweight but extremely strong. The material also has very good memory, meaning it will spring back to its original shape. The foams are closed cell and won't absorb water. All materials used are very durable in a harsh saltwater environment. The EPP foams are widely used in other industries for its resiliency. The Abrasion Shield on the front surface is overmolded with an elastomer to provide additional grip against the target. The substrate of the shield is an impact-resistant ABS plastic, so whether the target is a ship or rocks, it will hold up. Even with a complete failure or destruction of the shield, the system will still function and protect the bow of the craft and allow for personnel to move across it. A quick static analysis of just the standard EPP foam section shows that the max stress in the foam is only 1.5 megapascals with a 6,000 pound load, resulting in a factor of safety well over 10. So in summary, we believe this solution has met all the requirements. It's simple, but very effective. In addition to the stated requirements, we feel we have gone beyond those by ensuring that it's manufacturable at a reasonable cost. We always try to think ahead in our development programs to take into account how it will be made and what type of capital will be required to get it into production. We also feel that the fact that this product is nearly indestructible makes it a clear winner over any of the other ideas we generated. With a pneumatic system, if it's punctured, shot at, or leaking, you will not only lose protection to the bow, but you will lose stability for the operator to cross on. The design can really take a beating, and although you may lose aspects of it, such as the abrasion shield or a corner of the foam, you'll still retain bow protection and a stable platform for the operator to get through the mission. We've included the 3D models and an assembly drawing with the bill of materials along with this presentation. If there are any questions, please don't hesitate to reach out, and thanks for the opportunity.